Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. Okay, let's unpack this. We're starting our deep dive into the absolute foundation of electromagnetism, electric charges and fields. Our mission today is simple. We want you to gain such crystal clear conceptual mastery over the basics that you feel, fully confident tackling the material ahead. Tell me, have you ever taken off a sweater or maybe a synthetic shirt in very dry weather, maybe in the winters, and you hear a crackle? Or maybe even see a tiny spark. When nothing is actually touching, why does that happen?
Yes. It is quite surprising. That happens all the time. Sometimes even just opening a car door gives a tiny, sharp electric shock. It's actually, well, it's definitely memorable. I always thought it was just friction, like rubbing two things together. But I still don't really get why the friction creates electricity and why does it jump through the air?
That is the perfect question to start with. The reason is the sudden discharge of accumulated electric charges. That's what we call static electricity. And here is the historical fact that makes this subject so fascinating. The very word electricity comes from the Greek word electron, which means amber.
Amber, like the fossilized tree resin.
Exactly that. Thales of Miletus, around 600 BC, he observed this basic effect just by rubbing amber with wool. And he noticed it attracted small, light objects. For centuries, this simple observation was a deep mystery. It asked the ultimate question that defines this whole unit. How can two things push or pull each other without ever touching? That invisible property. That's the electric charge. And understanding its nature is our main task today. So let us start with the core idea. Electric charge is not something exotic. It's the most fundamental property of matter, just like mass. If mass is what determines how objects respond to gravity, then electric charge, well, it determines how objects respond to electrical forces. Everything you see is made of atoms, and those atoms contain positive charges, the protons, and negative charges, the electrons. But the difference between charge and mass is critical. We must anchor this idea right now. Think of gravity like you are on a cosmic one-way street, a one-lane highway. Every piece of mass only knows one destination, attraction. You are always being pulled.
And charge is completely different because of repulsion. That's the real mystery, isn't it? How can something have a property that makes it actually push away from its own kind?
Exactly. Electricity is the universe's two-way superhighway. The force field is the road itself. But you have two distinct kinds of traffic. You have positive charges flowing in one direction and negative charges flowing in the opposite. They attract the opposite traffic because they want to neutralize, but they absolutely repel their own kind. The difference is vital. Mass always attracts. Charge can attract or repel. That duality, positive versus negative, is the foundation of electromagnetism.
That two-way street analogy makes sense. So it clarifies why charge transfer is so important when we rub objects. When we rub, say, a glass rod and silk, we aren't creating new traffic. We are just shifting the existing electrons from one object to the other. One material ends up with a surplus of negative traffic and the other with a deficit, which makes it positive. It's all about creating an imbalance, right?
Perfectly put. And yes, Benjamin Franklin is the one who defined that duality. He names the charge on the glass rod positive as the standard convention. Now let's lock that idea down with a quick mental picture so you never forget this duality. Picture this fundamental property as invisible electrical badges. Electrons wear a negative badge, protons wear a positive badge. When two badges of the same type come close, they repel, like enemy armies refusing to share space. But when opposite badges meet, they attract, like Romeo and Juliet. This badge creates an invisible force field around the particle. We'll define that precisely as the electric field later in the unit.
Wait, I have a doubt. If this property is so fundamental and creates such a strong force field, why is the electrical force so much stronger than gravity? Gravity also comes from a fundamental property, mass, yet a tiny spark can overpower gravity completely.
That is a phenomenal question, and it highlights the sheer power disparity. The electrical force between two protons is about 10 to the power of 36 times stronger than the gravitational force between them. Gravity is usually only observable when one object, like a planet, has a massive, uncompensated amount of mass. Electrical force, on the other hand, is active at the particle level. It's the dominant force in the universe, until objects become neutrally balanced. That strength is why we must study this in depth. Okay, now that we have established the conceptual idea of charge and its duality, let's move from the simple analogy to the formal language. The language required for, conceptual mastery. We need a precise vocabulary for the exam.
So if we want to talk physics formally, we need a precise term for charges that aren't moving, right? What did NSERT call that specific field of study?
Very good. You've sensed the flow perfectly. Now, please read the formal definition of the unit, electrostatics, for us.
Quote, Electrostatics deals with the study of forces, fields, and potentials arising from static charges.
Notice the key word there, static. This whole introductory unit is about charges at rest. If the charges start moving, we switch to current electricity, a different chapter altogether. We must also remember that the property differentiating the two kinds of charges, plus and minus, is formally called the polarity of charge. And this polarity, established by Franklin, dictates whether the force will be attractive or repulsive. Now let's trace the steps of charging a body, which NCERT covers next. Step 1. To electrify a neutral body, we must transfer charge. Crucially, in solids, only the loosely bound outer electrons transfer, not the tightly locked-in protons. Step 2. If a body loses electrons, it means it has an excess of protons, so it becomes positively charged, like the glass rod. If it gains electrons, it has an excess of negative charge, so it becomes negatively charged, like the silk cloth. And here's the concept of conservation. No new charge is created. The total charge in the system, the glass rod plus the silk cloth, is simply redistributed. If the rod loses 10 electrons, becoming plus 10, the silk gains exactly 10 electrons, becoming minus 10. The net charge of the isolated system remains zero. This is the law of conservation of electric charge. This mechanism of charge transfer leads us directly to the behavior of materials. This is crucial for handling electricity safely. Some substances allow charge to move readily. These are conductors. In others, they resist it. Those are insulators. What makes the difference? It's the free electrons. Metals like copper or aluminum, the human body, the earth. They're all conductors because they have free, mobile electrons ready to jump. Insulators like plastic or glass have tightly bound electrons which cannot move easily.
This helps me understand the earlier scenario. If I rub a metal spoon, it doesn't hold a charge like a plastic comb does.
Yeah.
Why does the charge on the metal immediately disappear when I touch it? Is the charge destroyed?
That is the most common conceptual block we see. No, the charge is not destroyed. It is simply transferred or leaked. You see, since both a metal spoon and your body are conductors, the charges you generate immediately leak through your body to the ground. The ground is also a massive conductor. The earth just absorbs the charge, effectively neutralizing the spoon instantly. The plastic comb, however, works because plastic is an insulator. The charge stays exactly where you put it. It's trapped on the surface and cannot easily leak away. That is the fundamental difference that controls all circuit design. Hope everything is clear so far. This concept explainer is supported by ProfSam.com, helping you master 12 CBSE concepts. Let us look at another core property of charge required for the board exams. Additivity. We treat charge very simply in terms of magnitude. Charge is the scalar quantity, just like mass or temperature. It has magnitude but no direction. That means we add charges algebraically, using their signs directly. If a system has multiple point charges, say a small volume containing plus 5 coulombs, minus 3 coulombs, and plus 7 coulombs, the total charge is simply the algebraic sum. Plus 5 plus 3 plus 7 equals plus 9 coulomb.
So we just treat the positive charges as income and the negative charges as debt, and we find the net financial balance of the system. It sounds very straightforward compared to adding vectors.
Exactly. It is straightforward because charge itself is a scalar. This fact is vital for two reasons. First, it simplifies calculating the total charge. Second, it allows us to easily distinguish between the scalar quantity, charge, and the vector quantity it produces, the electric force or the electric field. The resultant force will be a vector sum, but the underlying charge that causes it is just a simple scalar number. Understanding these properties, especially duality, conservation, and additivity, is the essential prerequisite. This conceptual clarity sets the stage for our next major topic, Coulomb's law, where we will put a precise number to exactly how strongly these charges push or pull each other across space. Now let us tackle those silent killers, the small, tricky points that often confuse students and, well, cost marks in the exam. We call them misconceptions. Killer misconception number 1 relates to conductors and current speed. Many students believe that electrons in a conductor must flow incredibly fast because when you flip a light switch, the light seems instantaneous. Wrong. In fact, the individual electron drift velocity is extremely slow, often less than a millimeter per second.
Wait, a millimeter per second? That's slower than a snail. Why does the light turn on instantly if the electrons are just creeping along?
That is the trick. The critical factor is not the speed of the individual electron, but the sheer astronomical density of available free electrons in metals. A number so huge it compensates for their slow individual creep. You have around 10 to the power of 28 free electrons per cubic meter. When you switch on the current, the initial electrical impulse, the field, propagates near the speed of light, instantly pushing all those millions of free electrons simultaneously. So remember this hook. The electrons creep, but the overall signal or the electric field propagation zooms. It zooms because of the sheer quantity of free electrons involved. You must not confuse the individual electron speed with the speed of the current propagation. Okay, killer misconception number 2. Assuming an uncharged object has no charge at all. Wrong. This is fundamentally incorrect. Every object always contains huge amounts of both positive, that is protons, and negative electrons charge. You, me, this table, we're all packed with charge.
I see. So uncharged simply means the charges are perfectly balanced, equal positive and negative, resulting in a net charge of 0. Charging an object is about creating an imbalance, like shifting money between two accounts, not creating charge from 0.
That is the perfect analogy. You are simply moving existing electrical money around, creating a surplus in one place and a deficit in another. To anchor the 4 core properties of electric charge, we need a strong mnemonic. Remember the mnemonic QUAI, quantized, unchanging, which means conserved, additive, and invariant. Let's quickly touch upon that invariant property. It's often listed but rarely explained. Invariance means that the magnitude of electric charge on a body does not change, regardless of the body's speed.
Why is that significant? Doesn't the mass of a body increase as it approaches the speed of light, according to Einstein's relativity?
Precisely. You have caught the conceptual link. Relativistic mass changes with speed, but electric charge is unique. It is frame independent. If an electron has a charge of -e at rest, it still has a charge of -e when moving at 99% the speed of light. This stability makes charge an incredibly fundamental and reliable constant in physics. A great phrase to cement these ideas is, charge quantizes, conserves, and adds. Never created, never destroyed, just moved around. For a physical anchor to remember conservation, hold your hands apart now and pretend to move charge from your right hand to your left hand. This gesture shows conservation. The total amount of charge held between your two hands stays the same, even though you're transferring it from one to the other. To summarize our introduction today, let's look at the 3 main takeaways you must remember for your conceptual exams. Summary point 1. Electric charge is a fundamental property of matter. It exists in 2 types, positive and negative, which are responsible for duality. That is, they can attract or repel. Summary point 2. Charge follows 3 essential rules. It is conserved, meaning the total charge in an isolated system is constant. It is additive, so charges sum algebraically, and it is quantized. It only exists in discrete integer multiples of the elementary charge, E. And summary point 3. Materials are fundamentally classified based on electron mobility as conductors, where free electrons allow charge movement readily, or insulators, where bound electrons keep charge fixed. This distinction determines how we control and harness electrical energy. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, exactly. ProfSam.com. Thank you for joining us for this deep dive. Stay curious.